Hi, everyone. Thank you for coming to this talk. The title is Not Your Father's Database, How to Use Apache Spark Properly in Your Big Data Architecture. This talk could have just very well been named, but it wouldn't have been as fun. Not a database. And if there's one point that you leave this talk with, it's to understand that even though you can use Spark SQL with Spark, it's not going to have the same properties as a regular SQL database. And I'll go into more about that. But first, I just want to tell you a little bit more about me and how I ended up at Databricks. In 2005, I joined Google as a software engineer, and I worked on two major projects while I was there, mobile restrict web search, and then also voice search. So both of these projects involved running MapReduces all the time on a cluster of over 1,000 machines. And this was just something I did every day. I woke up in the morning. I used to joke around that my previous job in my previous life was to be a MapReduce babysitter. Voice search in particular, to build the kind of, it's the product, I don't know if you guys have used it, but it's on the Android phones. Every time you click into a button, does speech recognition of whatever spoken query that you're doing, and then it hits a Google web search. So in order to build those models, they actually crunch through a full years of English US Google data. So that was what my life in 2005 at Google. I worked there for 5 years, and then I left. I went to a couple startups, and I found myself in 2012 at Square working on reporting and analytics. And at the time, Square was a very, very promising startup still, a very extremely intelligent, talented engineering team, and I was building reporting and analytics on sharded MySQL databases. And Square has some big data technology, but I just saw how hard it was for a startup to get started with Hadoop infrastructure from scratch. Everything from provisioning a cluster, the libraries were clunky and hard to use and other things. And so I realized that if Square has a hard time doing this, a lot of companies must have problems with that. And that's when I started learning more about Spark, and I got interested in Databricks, just because I was impressed with just how advanced Spark technology is with the in-memory caching and other things, how elegant the libraries were. And that's what inspired me to come to Databricks and be a solutions engineer, where my current job is to help a bunch of customers get up to speed and start learning to use big data infrastructure. So to start, I just want to ask a show of hands if this is what your Spark infrastructure looks like. So this is a simple kind of Spark system where you have HDFS or S3 or some kind of file system. You've attached it to a Spark cluster, and probably you use SQL to query that data. How many people use Spark for this purposes? Great. So this, all my customers at some point start out, at least, with their data infrastructure looking something like this. And the system, if you notice, I drew a black box around it. If you look at that black box, it talks a lot like a regular SQL database, but the performance is very, very, very different in this particular system. Spark, just attached purely to a file system. I'd like you to think about that when we go through the talk today about different use cases. When you're having Spark just write out to just flat files in a file system, how the performance is going to be different than a traditional SQL database. So given that just a database isn't enough with just talking to Spark, or sorry, a file system isn't enough to talk to Spark, what should Spark look like in 2016? Well, there were some major initiatives that happened in Spark in 2015, and now not only can you have Spark talk to a simple file system like HDFS, but you can have it talk to your traditional SQL databases. My favorites are Postgres and MySQL. All your NoSQL types of databases, be it HBase, Cassandra, Mongo, and others. Specialized engines like Elasticsearch, and even live message queues like Kafka and Redis. And this is just some. There are many, many, many more. And the major initiatives in Spark in 2015 that enables this kind of functionality was the introduction of the Data Frames API, and paired with that was a Data Sources API. So all of these different Postgres, MySQL, other things, they've implemented the data source API, which essentially allows you to read from those other types of data sources, but still use Spark SQL, still use the same Data Frames API against data in those data sets as you would use with just your regular files in a file system. And there was also Project Tungsten, which makes sure that Spark just runs super fast, close to bare metal, with these kinds of different data sources. And my goal for everyone today is to know when to use other data stores besides just file systems. So when you're going to use Spark and you're trying to find a place to dump your data, file system is oftentimes a great place to put your data, but there's sometimes where it makes sense to put your data into the other places. Spark won't eliminate the need for all of those data sources that I listed on that other slide. So what's good for file systems for your data? It's a great general purpose processing if you want to do it against a really large data sets. So the types of data sets you want to store in file systems that I find are very common are things like archival data. So we have a lot of customers that have a lot of old legacy data. One, they just don't feel comfortable with throwing it out. They think it's too valuable even if they don't often process it. Or maybe even they just only actually do a computation against that old data for once a year or other things. So taking all that archival data and dumping it to a file system where it's really cheap makes a lot of sense. Another data source type might be unstructured data. In that case, you may not get a lot from writing it to a database or other kind of more specialized data source algorithm just because your data doesn't have structure. So a lot of the optimizations that databases can typically do may not work as well on your unstructured data. Another is social media and other web data sets. Those are just such humongous data sets. Again, the reason why you're putting in a file system here is it can be cost prohibitive to stick elsewhere. And the fourth one is for having backup copies of your data stores. So I have a lot of customers that they use a database. It's great for querying and servicing their website. But when they want to start doing some more advanced analytics, advanced aggregations, machine learning or other things against that same data that they have in the data store, their database doesn't perform all that well against it or may not even support certain kinds of computations. So what a lot of customers will do is they'll do a nightly or weekly snapshot of that particular data store of their whole MySQL database, dump it into files, and then use Spark in order to process that same database. So you might even store, as you see, your data in multiple different places. The kinds of workloads that you can handle well with files with Spark is batch workloads, obviously, like nightly jobs or hourly jobs to perform aggregations or reporting or other things. A lot of ad hoc analysis as well. So especially with Spark, because you're using in-memory caching, if you use that as a best practice, you can get back to just a few seconds of query time to go against your data set. So, when I was talking about Google in 2005 running MapReduce's ad hoc analysis wasn't a great thing to use against that because the jobs themselves would take 10 minutes just to launch. But with Spark, if you cache things in memory, you really can just explore your data live while you're there. Another use is multi-step pipelines. So perhaps you just have a bunch of different stages of your ETL or other things that you want to do. Using Spark against a file system is great for that. And maybe a more specialized use case is iterative workloads. If you're trying to run an ML algorithm against your data set and you have to run multiple iterations of your data, using Spark on a file system works great for that purposes. Some of the benefits you're going to get with using a file system to store your data with Spark is that it's extremely inexpensive, as I mentioned, in terms of storage. You're still going to get incredibly flexible processing with Spark. So there's, tons of different computations that you can do. And what you're going to get is not only the ability to scale and dump more and more data, but as long as you keep your Spark cluster sizes growing with it and you've written your job correctly, you can even keep things up in terms of speed. What's not so great with Spark connected directly to a file system is if you do very, very frequent random access. So let's consider the SQL query here. Select star from my large table where ID equals some random integer. Will this command run in Spark? It definitely will, but it's not very efficient. So if you think about what Spark's doing when it's reading data from flat files, is it reads all the files in, searches through it linearly until it finds that particular ID, and then returns it to you. So, that's just not all that efficient. What's the solution? If you're doing, this is fine. If you're doing ad hoc analysis and you're searching for something, this is fine. But if you're doing this in terms of queries per second, because you're trying to, find data to service a report on your website to your end users, you don't want to use Spark just attached to a file system from that. This is just a common classic use case for a database. For traditional SQL databases, oftentimes you'll have to create an index on the particular key column that you're trying to query against. For key value NoSQL stores, those obviously just retrieve the value of a key efficiently out of the box. So another thing to think about with Spark when you just use a file system to store your data is that are you doing frequent inserts? Because that's not going to work so well with just a file system. So an example of this query, Spark SQL, insert into table my table, select fields from my second table. What's going to happen here is every single time you do an insert, it's going to create a new file to just write all that new data into the folder where your Spark SQL table contains its data. So these inserts are reasonably fast. It doesn't take that long to write out a single file. But if you're familiar with Spark query speeds and optimizing it, if you have 50,000 few kilobyte files, that's not going to query so fast into Spark once you're actually trying to read all those things in. The bottleneck for your Spark job will be opening file handles and reading files rather than really the data processing that you want to do. So what's the solution here? Well, option one, if you're doing queries per second, again, of inserts, a whole bunch of them per second, just use a traditional database in order to support these types of inserts. That's what a database is used for. Option two, for me, sometimes I still will want to use Spark SQL to, I have a common use case I do. Let's say that I run a nightly or hourly batch job. I might want to insert some data about how that batch job ran into a Spark SQL table, and I don't want to fiddle around with having to set up a SQL database in order to do that. So I might just actually insert that into files into Spark SQL. That's totally fine, but what I do is routinely every now and then I'll run a job to kind of compact that table, to take all of those 10 or 20 or 100 files that I've written out and make it into a single file, since it's still going to be a reasonable size. And that's a pretty simple Spark SQL query. You can just do a select star from your table, run a .coalesce command on the resulting data frame, and then save that back out as another table that will be a compacted form of that. So two ways to deal with this, work around this frequent inserts, if that's what you're trying to do. The other thing that is Spark works great for with data in files is if you're trying to do a lot of data transformation or ETL. So in particular with Spark, it can read in data from all sorts of different data file formats. These are just some, but it works great for reading in log data, JSON data, CSV data, writing out to Parquet files if you want. You can zip your files. Spark has built-in libraries to work with all these different file formats, and you can really splice and dice your data any way that you'd like. One new thing to note, if you're from a traditional SQL database type of world, is that because file storage is so cheap, when you're using Spark with just attached to HDFS or some kind of file system, it's not an anti-pattern to duplicately store your data. If for whatever reason, for the way you're processing your data, it makes more sense to store it in a different format, store it both ways and get that kind of optimization. What Spark with a file system isn't so great for, though, is if you do frequent or incremental updates. In fact, if you go to Spark SQL, you'll notice that update statements as of Spark 1.6 aren't actually currently supported. And let's think back about why not when you're writing in data from files. Some of these things we already talked about. Let's say that you did want to update a particular row within your flat files. Well, the first thing you're going to have to do is find and locate that row within the file. And we just talked about how random access isn't very fast with Spark against a file system. Then the second thing you'll have to do is either you'll have to delete that row and insert a new one, or you'll have to update the row within the actual file. You'll have to do one of those two options. So, we talked about how inserting isn't so great. Deleting in the middle of a flat file, a lot of the file deleting or updating within a flat file, the file formats that you're trying to use, like CSV or JSON, they're not optimized for supporting that kind of update of your rows. So you can see why it just wouldn't be so efficient or work so well. And the solution here is if you're frequently incrementing or changing your data, a lot of databases support these update operations, obviously, very, very, very easily. One use case that I'm seeing a lot that's kind of mistake with a lot of customers. I mentioned the use case where customers are dumping out their production SQL databases into files and then accessing that with Spark. So they'll have that on a nightly batch job, and now they want to have their data more up to date than just every night. They want to get data live of what their databases look like. So I saw a lot of customers that were asking about the ability to update, because what they want to do is have their snapshot of their database at night, then send over the same update statements that they're making to their live production SQL database, also send it over to Spark SQL so that Spark SQL gets those updates live. That's not how I'd recommend if you did want to have a fully live view of your SQL database to access it by Spark. So instead, what I recommend doing is if you take a database snapshot of your database, and then you'll have to do an incremental SQL query to just grab the rows that have changed since that last snapshot. So you will have to have timestamps to denote when a row changes. You'll have to think of a way to figure out how to detect if rows have been deleted and other things. You'll have to get that kind of logic done. But once you do that, it's just a matter of almost joining your live snapshot with your most current views of your rows and then figuring out what the most up-to-date row is. So that's an operation you could easily do within Spark. I did want you guys to know that that's the right way that I would build out the system. And there are currently a couple of tips that I could recommend for making this work fast. Because as you notice, your database snapshot, the number of rows there, they can be pretty large, your database snapshot. So if you have to do a full shuffle of that database snapshot every time you want to join with a new live update, things could get pretty slow. So there's a new command, it's called cluster by in Spark 1.6 that you can use to cache your database snapshot so that it's already pre-shuffled according to the ID that you're trying to join by and leave that in memory. So if you guys all sign up for the Databricks Community Edition, if you go to the Databricks Guide and you go to the Spark SQL folder, you'll see a notebook that's called Cluster By, and it'll explain that optimization. And I recommend reading about that. Another thing to know that's likely coming up in Spark 2.0 or one of the future Spark releases is the support for bucketing. So that's going to allow you to take your database snapshot, write it out to files where it's pre-shuffled, and then use that to join your SQL. So both of these optimization techniques will make it easy for you to do the join to support this particular use case that I see a lot efficiently. The other thing that Spark is great for is for connecting your BI tools. So we have a lot of customers, they have data that they want to read into some kind of BI tool. Tableau is very popular, but that data set, it's too large to import directly entirely into Tableau. So instead of writing all your data directly into Tableau, you can have Tableau point to Spark and then have Spark read in your data from your data files, and then you'll be able to utilize all the cluster and distributed system properties of Spark to analyze a larger data set. So this works great, for your internal use cases where you have your own internal reporting or other people within your company that are pointing to Spark. And obviously, all the regular kind of tips that you would do within Spark SQL to make your queries faster, you'll also want to do if you use this method. So things like just caching your tables for optimal performance. But if you do joins and other things, you'll also want to just run those through Spark SQL and see how to optimize it. What doesn't work so great with Spark is if you're against a file system is if you're trying to serve external reporting under high load with Spark. So let's say that you have a whole bunch of different end users, queries per second, coming to your website that wants to query a certain data set. Would you point them directly at Spark and have them read files into HDFS? That's not going to work so well, because the way that Spark works is you get your first request for a query, it gets scheduled onto the Spark cluster to run on the distributed system, and then as you keep coming more, if those don't return before the previous job doesn't return before the next job comes, eventually your jobs are going to start to queue up and just kind of slow down the whole system. So Spark is meant to be fast for one individual query, but it's not supposed to handle 100 different queries in a second at a particular time. So if that's what you're really trying to do, what you want to do is read in your data from your files, aggregate them with Spark, in whatever way that you want to serve to your end users, dump that out to some kind of database, and then point your users to actually query that database. And a lot of databases are obviously optimized to handle actual production queries per second type of workloads. The other thing that Spark against a file system is great for is doing machine learning and data science. So you can use MLlib, GraphX, and also Spark packages for machine learning or data science. So again, you have data in files, you want to do some more advanced kind of algorithms against it. The benefits of using Spark is that you're going to get built-in distributed algorithms already so that you don't have to recode those things up. You'll have in-memory capabilities for your iterative workloads, meaning that if you're running a machine learning algorithm that has a whole bunch of different phases, it's going to keep that data in memory so it keeps running really fast for all those things. And the other thing is that it's going to be an all-in-one platform. So a lot of machine learning types of libraries will only allow you to train a model. You'll have to figure out your own ways to cleanse your data, to featureize it, to test it. So all the data cleansing, featureization, full end-to-end, you can do all of those things within Spark. And also, I hope that all of you are familiar with Spark packages. It's a community-driven website where we've posted, anyone in the community can post a particular library or package that they think would be useful to the open source community. And a lot of the data sources API to support connectivity to all the different data sources that we saw, those are all a part of Spark packages, but there's even more advanced machine learning algorithms. There's even packages to analyze very specific types of data sets. So if you haven't checked out the Apache Spark packages website, you should definitely do that. What Spark against a file system, though, isn't so great for is, again, if you're trying to search for content under heavy load. So I wouldn't use Spark to take the place of a search engine. If you do the SQL query, select star from my table where name like % some string, that's definitely going to run within Spark. And if this is a query that you're doing during ad hoc analysis or exploration purposes, internal purposes, infrequently, you can get this to return in every few seconds. But if you're servicing live external customers of yours, you expect queries per second. If you point this at Spark, it's not going to go so well. And it could go through each row to find results. That's one particular problem in the same load. So if this is the kind of workload that you're doing a lot, you'll want to consider using Elasticsearch or Apache Solr or some other kind of specialized algorithm. Great. And that's, I hope that today's talk's just given you a feel for alternatives to storing your data when you use it with Spark than HDFS and S3. I think for coming to the talk and open to questions.
So my first question is, sounds like you would recommend Spark over Hive to query HDFS, and could you explain why? And the second question is, I'm very confused about one of your slides. You're explaining you take snapshot of the database and apply the SQL query to update that, then use Spark to query. Like, why do you do that? Why don't you just query the database using SQL? And, yeah.
Okay, let me get to the first question, which is, I think that Spark SQL has the same functionality that you'd get with Hive. I don't really see a lot of advantages of using Hive over Spark SQL, or that I know of. There's no functionality in Hive that isn't supported in Spark SQL. You could still do, the reason why people used Hive is because they wanted to be able to do SQL syntax type of queries on top of Hadoop. So it's the same thing. If you want to use Spark as opposed to Hadoop, then you'll also want to use Spark SQL over Hive. So that's a simple one. The second question of this particular slide here, lots of times the reason why my customers are using the database snapshot plus the incremental SQL query into Spark is they're trying to do some kind of query or some kind of computation that their SQL database itself doesn't handle very well, are very fast. And so they want to be able to access that data in Spark. So it could be because they want to register a UDF. It could be because they're trying to run machine learning against it. It could just be because they're trying to do some kind of aggregation on top of their database. SQL works well if you're trying to access specific rows. If you're trying to do some operation that requires reading in all the rows in the whole database, it can take pretty long in a lot of SQL databases. And so having the flexibility of being able to read that into Spark works really well. I'm sure the open source team has. I personally have not. Spark SQL, you'll have the added flexibility of being able to cache your data in memory. So if you do that, then your query should go a lot faster than if you used Hive with just regular Hadoop, reading data from files every single time.
Hi, thanks for the presentation. So a couple of slides you have explained that whenever you are running the interactive queries, there are limitations in terms of concurrency and in terms of the number of, the query that you are pulling out, etc. But most of the Spark's advertisement, as per se, says that it is a single shop tool for interactive, real-time, and batch. So where does it fit in that interactive queriness? Because one of the main requirements for us is many decision scientists are running the queries concurrently, and we need the result concurrently. So if it is not supporting, is it not a big drawback?
No, so Spark runs great in terms of being fast for doing individual queries. What you don't want to do is point Spark attached to a data system and then do like 1,000 queries per second against it. So it's a more extreme use case, right? Like even traditional data warehouses, they don't do well if you have more than a certain number of queries that are going out at a given time. So if I had my website, if I had a retail website and every single time someone came to a page, they're querying the database to figure out the current catalog of things on my site, I wouldn't use Spark attached to a file system for that. You just want to continue to use a traditional database.
But are you saying that many different decision scientists can run different queries against the Spark? Is that supported?
That's definitely supported. And another thing to consider is to launch multiple Spark clusters for multiple different users. And that's one of the things about Databricks and the fact that it's in the cloud that makes it really easy is after, if you have all the time in the world, you can all use just a shared cluster. Sometimes it makes more sense to just have your own cluster to really bang at things if you're doing really heavy workloads.
Okay. Thank you.
Right now, we put our time series data in HDFS and manage those files and according to the time and manage them by ourselves. But we want to look for alternative tool to help us manage this data. Do you have any recommendation?
So what kind of data was it again?
Time series data, like
time
every
series
second and have a lot of data, something like that.
Yeah, I think there are a lot of, Spark Streaming supports time series data well, and there's a lot of specific libraries out there to support time series. I'd find out more about what other things people have already written to do that. But that's, a very common use case for Spark Streaming is to read in time series data from Kafka and to analyze it.
It was a great presentation, and you definitely answered the portion that comes from data that comes from HDFS, and then going to like a database, for example, and then querying it like this. But what about like getting the data in? Like you mentioned, like not a lot of inserts, but for example, like Spark Streaming, you might want to stream into S3 as like Parquet files, for example. So and then eventually do the batch jobs on that and the ETL on that data. So what would be like the best way to do that, or is that a good solution?
No, that's a great solution. So using Spark Streaming to read data in from a queue, and then less frequently, not every single second, but to write out a particular file, that's a great use case.
Okay, so like 5-minute delay or something like that?
Right.
Okay, cool, thank you.
Awesome. That's about all the time that we have for questions, but thank you, Vida, for your presentation.